Hello and welcome. My name is Torbjörn Nordling and I'm an assistant professor in automatic control at the Department of Mechanical Engineering at the National Cheng University, and I'm also the general chair of this workshop. Behind me I have the UH-1H helicopter that was donated by the Taiwan Air Force to NCKU. This helicopter has, during its 25 years of service, participated both in typhoon, mountain, and shipwreck rescue missions where it has saved lives. It's my pleasure to introduce our honorary chair, Chair Professor Wu, that will welcome us all to this workshop.
It is a pleasure to welcome all of you on behalf of the National Cheng University in Taiwan. I'm proud that our team, the NCKU Parkinson's Disease Quantifiers, are one of the finalists in the OpenCV AI competition. They are also arranging this workshop. Now let us all learn computer vision and AI using the OAK-D camera together.
I'm happy to tell you that we already have over 800 registered participants for this workshop series. You are most welcome to subscribe to our YouTube and Twitch channels, and also to press the alarm bell icon if you would like to be notified every time we publish a new video. It's my pleasure to introduce my good friend, Che-Wei Lin, Assistant Professor at the Biomedical Engineering Department here at the National Cheng University in Taiwan. Professor Lin is focusing his research on the application of artificial intelligence to challenging medical problems, and today he will be presenting on AI-assisted orthopedics. Please enjoy the talk.
Good afternoon, everyone. I'm Che-Wei Lin from Department of Biomedical Engineering, National Cheng University. It's my pleasure to present our study titled as AI-Assisted Orthopedics Development of an Explainable XCuffNet for Rotator cuff tier radiography classification today. Next, I'm going to present the highlights of the study. First, we developed XCuffNet for RCT classification and achieved 94.1 accuracy, which is outperformed the AlexNet, GoogleNet, and the ResNet 50 in our study. Second, by integration and the combination of machine learning techniques and the feature selection techniques, we found that AS type, AHI, HC, GT that define in shoulder radiography features is important and can achieve the classification accuracy of 92.2. Third, by applying the explainable AI techniques such as GBP, CAM, or Gray CAM, we found that the area between acromion and the humeral, acromion, greater tuberosity, and the glenoid can be adjusted by XCuffNet, and which also meets the clinical finding and the disease fundamentals of rotator cuff tier. The main contribution of this study are: first, we have developed deep XCuffNet for RCT radiography classification and it presents good performance. Second, the representative features in discriminate RCT radiography were visualized so that the physician can check if it is appropriate or not. Third, the representative features of the shoulder radiography features including AS type, AS size, AHI, HC, GT, and the GT spurts were used to classify rotator cuff tier. Fourth, in comparison with the existing literature, we achieved the higher risk AUC value of 0.95 in machine learning and the specificity of 95.3 in deep learning. Fifth, which is also the best, this study is the first study to compare the machine learning and the deep learning performance in RCT classification in the literature survey we have done so far. Next, we are going to the introduction of disease fundamentals of rotator cuff tear. It is the most common shoulder injuries, and in RCT subject, one or more tendons of the sixth muscle are torn. And you can see this is what we define as the sixth muscle area. And it leads to the rotator cuff tear. The causes of the rotator cuff tear, including the tendons violently stretched, or the same motion overuse, or also the elderlies. You can see that the prevalence of the rotator cuff tear increased with the age. For the population, there is almost several millions of the people suffer from the rotator cuff tear around the world. For the diagnosis of the rotator cuff tear in clinical medicine right now, arthroscopy or open surgery, MRI are the most important diagnosis of the rotator cuff tear classification. However, it takes lots of medical cost and a long time to wait. Compared to another generally seen techniques of the orthopedics, shoulder radiography, because it is not so good at the soft tissue examination, so it is not regarded as the golden standard of the diagnosis of the RCT. However, it has the advantage of the non-invasive, inexpensive, and obtained instantaneously characteristics. And also based on the experiments of some of the orthopedics, they found there are several incidents that can be used radiography as the input to classify the rotator cuff tear classification. So our study aims at using radiography as the features to discriminate RCT or not in our research. Based on our literature survey, we found that the radiography features such as acromion spur types, size, greater tuberosity morphology, GT spur thickness, and also acromion humeral interval and the Hamada classification, SPO classification are the features derived from the shoulder radiography that related to the rotator cuff tear, positive or negative. In this research field, we found that there are three main categories related to our study. The first one is that Kim and others used the shoulder radiography to discriminate RCT using deep learning algorithms. They achieved the 97.3 sensitivity and the 45.3 specificity. In their study, we think the specificity is not so good. In the other hand, Cheng and others used the MR image and also deep learning network to discriminate the RCT and achieve the satisfactory accuracy. In the earlier before, Lin and others and Lu and others used the variables extracted from the MR images and also some machine learning algorithms and achieved also satisfactory result. Although that several studies can achieve high accuracy using the MR image as the features, but our aim is to base on shoulder radiography, which is a very low medical cost and the instant way to get the image as our method. So we would like to collect the data in NCKU hospital and to start our research. Next is the research objective of this study. First, our study aimed to develop a deep CNN XCuffNet architecture in order to discriminate RCT radiography, and we would like to see what will be the comparison on their performance between deep learning and the machine learning approaches. In deep learning approaches, we would like to use not only our XCuffNet, but also the conventional and the state-of-the-art networks such as AlexNet, GoogleNet, and ResNet to compare their performance. Next, in the machine learning algorithms, we try to classify rotator cuff tear positive or negative based on 7 conventional shoulder radiography features that generated by physicians. So this will be the research objective of our study. Next, we are going to talk about the materials and algorithm flowchart of this study. First, all the data was collected in National Cheng University Hospital with IRB approval. In our database, we have total 102 shoulder images, which includes 59 subjects with RCT positive and 43 subjects with RCT negative. All the labeling results were made by physicians based on their endoscopy diagnosis. And also, in the right-hand side of these slides, you can see all the shoulder radiography features and the demographics of all our subjects in our database. In the next, I'm going to talk about the algorithm flowchart of this study. First, our input image is the radiography image. In our algorithm, we have 2 parts. The first one is deep learning parts, and the second one is the machine learning parts. For the deep learning parts, we will first do the image adjustment to do the crab and the flip activities. Then next, we will apply our self-developed XCuffNet and also compare the performance to the AlexNet, ResNet, and the GoogleNet. In the next stage, we will use the feature visualization approaches, including CAM, GradCAM, and the GBP, to visualize which features are focus area of our algorithm and compare to the clinical definition. This is the flowchart of the deep learning part. In the machine learning part, first, our physicians help us to extract following 7 features from the radiography data. In the next, in order to see the importance and the ranking, or we can say priority, of those 7 features, we use the feature selection method, including sequential forward and backward selection, and also NCA, to see who are the important features to achieve high classification accuracy. Then in the machine learning, we use the decision tree, KNN, SVM, and ensemble learning as our classification method. Then finally, we use the leave one out cross-validation to validate the final result and see the results. Okay, next, let's talk about the methodology and the result in our study. First, let's talk about the deep learning approaches used in our study. In our deep learning research, we not only developed the XCuffNet and compare its performance with AlexNet, GoogleNet, and the ResNet, we also did some feature engineering such as crab and the flip. For the crab, we cropped the image from the original raw shoulder radiography, just like the figure you can see in the left-hand side of the figure. Then for the crab feature engineering, we focus on the area that easily cause the rotator cuff tear and name them as the cropping image, as shown in the right-hand side of the figure. For the flip and the non-flip image is an original side view of the shoulder radiography which was taken by X-ray. For the flip image is flipping side view of the shoulder radiography to make similar side view for all data set which will be trained. If the right side view data set will be trained and all of the left side view data set will flip to the right and vice versa. In the classification stage, we compare the performance of the proposed XCuffNet to AlexNet, GoogleNet, ResNet in the rotator cuff tear radiography image classification performance. In our comparison, originally, we do the performance comparison on CNN without multiplication, then also compare the performance with modified CNN. The modified CNN was developed for feature visualization for class activation mapping. We remove the several layers in the network except last fully connected layer and the softmax layer, and add global average pooling before fully connected layer and the softmax layer, just like this. This is the explanation of the architecture of XCuffNet, which is the deep CNN for classifying rotator cuff tear radiography, which is also can say X-ray image, and it consists of 3 convolution layers from convolution 1 to 3 and the 2 fully connected layers. You can see the full architecture of the XCuffNet with original architecture and the modification for CAM architecture as shown in the figure. Next, this is the detailed description of each layer in XCuffNet architecture. Especially, I would like to explain the first convolution layer and the third convolution layer, which is responsible for extract low-level image and the high-level image, which is related to rotator cuff tear, respectively. The AlexNet, GoogleNet, and the ResNet 50 were utilized to compare the performance of the proposed XCuffNet. Those 3 CNN has 8, 22, and 50 layers respectively. In order to do the class activation mapping, you can see the architecture before and after modification of AlexNet, GoogleNet, and the ResNet 50 in this slide respectively. Those 3 networks were proposed in 2012, 2015, and 2016 respectively, and they are all state-of-the-art and very, very popular networks, so I think to compare with them is very representative. The feature visualization used is for the specific area activation to obtain the heat map. The focus area of heat map presents the feature learned by specific class, and it can find out the relationship between the featured and the predicted class. For example, after we apply the feature visualization in the example image, the focus area in the heat map can represent where the swing is from the original image. The purpose of using this is to understand the decision and the logic of the machine and the deep learning, so that after we apply the feature visualization in the rotator cuff tear classification, we can know that where is the focus area in the shoulder radiography and compare to the clinical definition to see if it is reasonable or not. In this study, we utilized guided backpropagation, class activation mapping, and a gradient-weighted class activation mapping (GradCAM) as our feature visualization method, and we will compare which is the most reasonable in compare to the clinical definition of rotator cuff tear in the later experiment result and a discussion. In order to evaluate the performance of the proposed network, we used sensitivity, specificity, precision, F1 score, accuracy, confusion matrix, and the area under the ROC curve, AUC, as our evaluation indexes. In our classification results, to compare the performance of XCuffNet and other CNN in the crop and the non-crop and in the original architecture and the modified CNN, our proposed XCuffNet can get the best accuracy no matter in the crop, non-crop, or original architecture or after modification. To summarize all the performance index, including accuracy, sensitivity, specificity, AUC, precision, and F1 score here, we can find that XCuffNet has better performance than other CNN, especially in the image without flapping. It has the highest accuracy, sensitivity, AUC, precision, and F1 score. XCuffNet is a solution method for rotator cuff tear radiography classification. Next, I will present the performance of the proposed network via confusion matrix and ROC curve. From the confusion matrix, we can find that the proposed XCuffNet misclassified total 6 cases out of 102 cases and outperforms than other networks, no matter in the classification accuracy and the ROC curve as shown in the figure. This is the feature visualization approach's result after we used based on XCuffNet and the ALXNet. From the XCuffNet, we can find that the acromion, greater tuberosity, area between acromion and the humeral were selected as the feature to discriminate the rotator cuff tear positive class. For the negative class of the rotator cuff tear, head, humeral, and the clavicle were selected as the important features and the focus features. In the ALXNet, we can find that the acromion, greater tuberosity, and the glenoid were also selected as important features, and the same as the head, humeral, and the clavicle selected as the important feature to discriminate the rotator cuff negative class. In the next part, I will introduce we used machine learning approaches to compare the performance of classifying RCT between deep learning approaches we proposed before. In the machine learning approaches, we present to use 7 shoulder radiography features, which is labeled by the physicians, and fed them into classifiers with feature selection method. Then let's see how the performance will be. In order to get what is the most important features in the machine learning, we used sequential forward selection, sequential backward selection, and the neighborhood component analysis as our feature selection approaches, and use 4 different kinds of model to compare their performance. In the feature selection, the main goal of the feature selection is to choose a number of features from the extracted feature set that yield minimum classification error. Then we use SFS, SPS, and NCA as our target. And you can see that there are 7, 4, and 5 features were selected from the SFS, SPS, and NCA respectively. This is the citation of the decision tree SVN, KNN, and also feature ensemble learning in our classification model. Based on our conclusion, we can find that AHI, AS type, HC, and GT has high feature selection weight in NCA and selected as the representative features in both SF and SPS, and also nearest component analysis. From the point of view of the classification accuracy, we can find that in the support vector machine, it can achieve more than 92% of accuracy. These are the old details of different machine learning models and the feature selection results in the accuracy, sensitivity, specificity, AUC, precision, and F1 score. We can see that the support vector machine outperforms other networks here. Also, based on the confusion matrix point of view, we can find that there are total 8 cases misclassified out of 102 cases, and in the ROC AUC curve, we can find that the Gaussian median filter of the SVN serve as the best performance here. In our research, we also make a little study about to extract shoulder radiography features from our shoulder radiography image. In a previous study, it is done by physicians. In here, we can see the summary of how we do that. In general, we utilized machine learning and deep learning approaches to achieve our goal. Take the acromion humeral interval measurement as an example. First, after we input the feature, we label the image by the different areas. Then we use the holdout validation and also combine with the deep learning segmentation method and get the result. After those results, we try to find the measurement such as the acromion humeral interval from the segmented final result. So based on those measurements, we can find the final result just like this to find the minimum distance of any of the two objects to get the measurement. Then we compare those shoulder radiography features, or we say measurement, to the physician's result. Then we can find that we successfully developed the algorithm to extract acromion spur type, SPO classification, acromion humeral interval, Hamada classification, and the greater tuberosity morphology. Among of the features, we found that we can do good job in the SPO classification and also the acromion humeral interval and the GT morphology. For others, we are not satisfied with the accuracy so far. Next, let's go to the discussion part. First, we compare the deep learning and the machine learning algorithm that developed in this study. We found that the deep learning XCuffNet outperforms every other approaches in rotator cuff tear classification. It achieved the accuracy of 94.1%. In the machine learning approaches, both the features from all and the features selected from the sequential forward selection can achieve the classification accuracy around 92%. To compare our study result to other similar approaches, we want to compare our study with Kim and the Shim study, which all published in 2020, and they are all related to using the deep learning algorithm. First, let's use the input as the first comparison. Both our study and the Kim study, we use shoulder radiography as our input feature, and the Shin use the MR as their input feature. So that means for Shim study, they need to spend more medical cost and time to get the MR as the input features to their classification model. For the image acquisition, I mean this is the standard how the physician to label this image belongs to rotator cuff tear, positive or negative. In our study and the Shim study, we all use the orthoscopy as the labeling basis. And in Kim study, they use the MR and the echo, which is the ultrasound, as their basis to label the result. However, to use the echo is not a very standard in the rotator cuff tear classification because it relies heavily in the technician's technique. So we are afraid that maybe this is one of the reasons to make so poor specificity in Kim's study. Finally, let's compare to the result. Our result outperforms both Kim and the Shim's result in the point of view of the accuracy, sensitivity, and the specificity, especially that Kim's specificity is very low. We are afraid that this is because in Kim's study, they recruited their samples from many medical centers, and they have around 8,000 images in their training and validation set. However, that means the inconsistent labeling from different medical centers and the different physicians, which is maybe one possibility to make their specificity so low. In the machine learning part, we compare two other similar studies which published in 2014. In those two studies, they all extract their features from the MR image. To compare the result, we outperform them in the AUC. We achieve the higher risk AUC. So we think that even though in the machine learning approaches, we can also outperform other two studies which published in 2014. In the next, we would like to discuss about the focus area from the feature visualization and also the features selected by the feature selection method in the machine learning. In the deep learning part, we utilize GBP, CAM, and the GradCAM to visualize the important features, including acromion, greater tuberosity, area between acromion and the humeral and the glenoid that related with the radiography in rotator cuff tear features for rotator cuff tear pathology, and visualize region in shoulder for non-RCT using AlexNet, GoogleNet, ResNet, and XCuffNet in both side view of shoulder radiography, no matter in right and left. In the machine learning part, by the three different kinds of feature selection approaches, we found that the acromion humeral interval and the acromion spur type and the AS size are the most three important features to discriminate RCT positive or negative. In summary, we found that the acromion spur type, acromion humeral interval AHI, Hamada classification, and the greater tuberosity morphology are the representative features of the rotator cuff tear radiography classification based on feature selection in machine learning based and the feature visualization in deep learning based approaches. In the next, we would like to discuss about the result of automatically rotator cuff tear radiography features computation. Compared to other two studies published in 2010 and 2012, we found that our automatically extraction of the acromion humeral interval is in the middle between the literature published in 2010 and 2012. And we found that our result is very similar to the result that labeled by our clinical physicians. These are all the 7 features we used in our study. The 7 features were labeled by our collaborator before, which is also an orthopedic clinical physicians. So far, we have done the 5 features out of 7 features in automatically detection. However, you can see that some of the classification result here is not very good. So we can say that if we want to automatically extract all of the 7 features and combine with the previous mentioned machine learning approaches in rotator cuff tear classification, this might be not so reasonable because the errors will be cumulated in 2 stages. Based on our previous result, we can find that by using the deep learning approach, we can achieve the accuracy of 94.1. In the deep learning part, we can directly input the features to the network. For the machine learning one, the total accuracy is 92.2. However, the feature used in the previous machine learning is extracted and labeled by the clinical physicians. That means this is not automatically extraction in the features. So if we automatically extracted features. In the average, the accuracy of the automatically extraction of our features in previous 5 out of 7 radiography features are approximately 75%. So after 2 stages of accumulation, we think that the accuracy will be much lower than 92.2%. So that means we recommend to use the deep learning and based on radiography image as the rotator cuff tear classification in the future after the study of our research. Finally, let's go to the last part, conclusion, limitation, and the future work. First, in our conclusion, the proposed deep convolution neural network XCuffNet outperforms other machine learning approaches in classifying rotator cuff tear and can achieve 92.2 and 94.1 accuracy in machine learning and deep learning respectively. Deep learning and machine learning algorithm in classifying RCT could achieve good accuracy, high sensitivity, high specificity, high precision, and high F1 score. Acromion spur type AHI, Hamada classification, and GT morphology were selected as representative features of RCT radiography classification by sequential forward, backward selection, and also nearest component analysis feature selection. The representative areas in classifying RCT radiography are acromion, GT, glenoid, and the area between the acromion and the humeral based on the feature visualization that correlates with shorter radiography features of RCT. The limitation and the future works of our study are: in the limitation, the number of the included data was relatively small. The radiograph side view of the included only image with anti-posterior shoulder views, and not all types of acromion spurs were included. The radiography parameters were measured by single orthopedic surgeon. These are our limitations. For the future work, we attempt that we can invite more collaborators after this workshop. If you are interested or you are orthopedics, then we can collect more data for our shoulder radiography and the radiography features data set to get higher performance and solve some limitations, especially in automatically radiography feature computing for RCT classification. Then we will continue to compute radiography features of acromion spur size and a GT spur thickness and combine all radiography features computing to be a system of machine learning based automatically RCT classification system. This is the acknowledgement of our study. The shoulder radiography and the features of this thesis and the study is collected by Department of Orthopedic team from National Cheng University Hospital. This thesis is part of the collaborator work from 3 clinical physicians, and we appreciate our sincere thanks to Dr. Hong Zhikai, Dr. Zhuang Haojun, and Dr. Che-Wei Lin in the study of this research. This is my presentation, and thank you very much. If you have any question or suggestion, please let me know in next Q&A session. Thank you.
Hello, Professor Lin. Hello, everyone. Welcome to join our Q&A session. Firstly, thank you very much for the great talk, and thank you for willing to join us online. So we have gathered all the questions from the YouTube chat. Let me to speak them out one by one for you.
No problem. Thanks for your introduction, and I'm ready for replying my questions. Thank you.
And the first question, hello, could you please explain more about the architecture of XCuffNet? Why can it perform a better performance?
I think because compared to AlexNet, ResNet, or GoogleNet, the original purpose of designing this network is quite different. We all know that the AlexNet, GoogleNet, or ResNet, they develop based on the database from the ImageNet, which contains thousands of different images and types of the object inside. However, compared to the radiography of rotator cuff tear, our image type is relatively similar. So we redesigned the architecture so it can best fit the view and the features of the radiography of the rotator cuff tear. So we think that's maybe the reason that we outperforms that of the AlexNet, ResNet, and the GoogleNet. However, as you can see, actually the accuracy is still very close. I mean that for the AlexNet, GoogleNet, or ResNet, it can perform also very well. Of course, because our net attempts to based on the features from the rotator cuff tear to do the optimization design, so we perform a little bit higher. So I think that's the reason why we outperform them. And the first and the third convolution layer, which to highlight the low-level features and the high-level features of the rotator cuff tear, I think are the keys to improve the accuracy of the proposed XCuffNet. Thank you.
Okay, thank you very much. The second question is, what is the output of XCuffNet? Can it give how severe of an RCT patient?
Thanks for this very good question. So far, the output will be only the binary result with the rotator cuff tear, positive or negative. So far, we haven't have the capability to output how severe the rotator cuff tear is. This is our future goal. However, compared to the existing diagnosis or study, there are only 2 teams around the world can, based on the radiography data, to predict the rotator cuff tear positive or negative from radiography. So I think we still have our competitive strengths on this because we based on the radiography, so low medical cost, and which is also can get the image very quickly, not necessary to wait for a long time, and we can predict the soft tissue injury such as rotator cuff tear. This is our competitive advantage, but I think we will working toward that more powerful XCuffNet that can predict the severe level of the RCT. Thank you.
Thank you very much. Next question. Can you suggest some methods in automatic extraction to increase the efficiency?
Okay, thank you. I think the in the segmentation part so far, I think our labeling results are not good enough. In the future, we will cooperate with more clinical physicians to make the area label in the shoulder radiography better, which can make our ground truth better. Also, in the methodology we use, we will compare several state-of-the-art deep learning or semi-supervised segmentation method to achieve better result in the segmentation of the features from the shoulder radiography.
Thank you. Next question. What is the difference of accuracy in the perspective of application? Is the 2% difference different a lot in the application?
Based on the discussion between our team and our collaborative clinical physicians, actually they don't feel too much difference between the 2% difference. However, we are engineering guys, so we care lots about the data. However, they think if the accuracy can over than 80%, that will be enough because the result of the XCuffNet is only one of the reference of the clinical physician. They will also care about other like symptoms or the evidence from other examination equipment and also the self-feedback from the patients. Then they did the final diagnosis result. So I think for a reference tool, the accuracy right now is enough. However, to achieve the higher accuracy is one of the mission of us, engineering guys. So we would like to see how to upgrade the accuracy better and better. That's my reason. Thank you.
For a great explanation. Okay, the next one is so far the last question. So for audience, if anyone wants to ask more questions, please just leave it in the chat. The next question is from Raven. Is cropping make it easier to focus on the region of interest, or the decrease of background make it more difficult to distinguish between background and foreground?
Thank you. Based on our study, first we think to crop in the arm-related part is can help to achieve the better accuracy. I think the one reason is that some of the feature in the background may affect the classification performance. So using the now so far we use the hand to crop the focus area, and in the future we will try to develop another small algorithm to make the cropping activities more accurate. So my conclusion is to use the crop methodology can get the better accuracy, and it can eliminate the effects of the background. Thank you.
Thank you very much. Okay, I think this is the end of today's workshop. Thank you so much for the answers. We will have another workshops at tomorrow 1 p.m. Actually, we have 2 workshops tomorrow. So for more information, please check our website. We'll put the link in the chat later. Look forward to seeing all of you. Thank you, everyone. Thank you, Professor Lin. See you next time.
Thank you. Thanks for Ren's introduction, and everyone. See you. Bye-bye.
Bye-bye.
Bye-bye.